Anjum, you can mute yourself.
Yes, sir.
This is Reshma. Hello.
Yes, sir.
Yeah, fine. We'll start the class. Okay, it's almost 10:10. We'll just continue up to plus 45 minutes now. Okay, could you able to see the video I just shared in the group? Hello.
Yes, sir. Yes, sir.
What is that video talking about?
Working of Mosfet, sir.
Okay, Mosfet exclusively what phenomenon?
Pinch of phenomenon.
Pinch of phenomenon. Uh, Basically, that is for what purpose? What is the purpose? Okay, what is that actually? When does pinch off will occur and all those things?
When the drain to source voltage is equals to saturation voltage,
Okay,
pinch of starts.
fine. Let us have a look at why I'm getting a echo sound from your side also. Okay, now this is the cross-section view of the MOSFET. So this is drain, source, and then you have the gate oxide, all those things. So this is MOS. Assume that this is a P minus. You have N plus here, and I not applied any. This is source. This is drain. Assume that I not applied any voltage. So this voltage is equal to 0 volt. Assume that this is Vg, which is greater than Vth, which is greater than Vth. So do you feel that okay, there will be electrons forming the channel between source and drain, Rishma?
Yes, sir. Yes,
Okay.
sir.
Now, if you can see in that what video, let me also share the what is that PDF of the textbook. Where is that? Where is that? Okay, it's here. What is that page number? Anybody can remember? 360. Let me just go to that. Mosfet amplifiers. I have to go somewhere here. Okay. Okay, I'm here. This is fine. Okay, here this is the thing. Can you able to see this?
Yes, sir.
Okay, let me increase that to this. Okay, this is a phenomenon what we are seeing. See here. When I just a minute. Okay, when does this will happen? Can you see this first picture, Reshma?
Yes, sir. Yes, sir.
When does this will happen? Can you see the what electrons are more here when it is coming towards the drain side? They are lesser in number.
Yes, sir.
Assume that. Okay, let me also share my. Okay, is this my camera visible now?
Yes, sir.
Okay, now assume that I have not applied any voltage. When I don't apply any voltage between source and drain, will I have a constant magnitude of electrons throughout drain to source? Whereas
Yes,
if you
sir.
can see here, this is not so over here. Can you see is it constant throughout the entire length of the channel?
No, sir.
Where it is less? Where it is
In
less? Where it is less? Can you see here it is more in terms of
more,
thickness?
sir.
More where?
Yes, sir.
Which is this terminal?
Source
Source.
terminal.
When you are moving towards the drain side, it is keep on reducing. So
Yes.
whereas in this particular case, let me also show my of course it is a bit intense in terms of understanding. Once you can understand this, okay, it is very easy. Now you can see between, okay, this is the gate structure. So when I apply only VG, there is no gate to source voltage applied. Can you see there is a potential from this gate to what is the other name for this? So shall we call this as, of course, this is a P minus substrate, correct?
Substrate. Yes, sir.
Substrate is the one over which we're going to have the source and drain diffuse so that you can have a MOSFET structure. So MOSFET structures are built on a substrate. That substrate is P minus for NMOS. So this we call it a substrate. So we will say there is a voltage between gate to substrate. Gate to substrate voltage is there, constant from this end of the channel to this end of the channel whenever there is no current flowing here. Whenever the current flowing through this channel is 0, we will have same electric field between gate and the substrate. So since the electric field from this end to this end in absence of this electron movement is same, we're going to have a constant concentration of electrons throughout the structure, because if you have some x volt per meter as a electric field, you're going to have the same x volt per meter on this edge of the channel also, because you have a channel length, no Reshma?
Yes, sir.
You
Yes,
have a
sir.
channel length. Over the entire channel length, the electric field is same, because we are not having any current flowing through this, because we are not applied any gate to source voltage. This gate to source voltage is 0. But when you start applying this gate to source voltage, so what I'll do is, whenever VDS is equal to 0, I will say this is VG from length 0 to, let me just, length L1. So assume that this is the length of the transistor L1 from length 0, that is starting from source end till the drain end. So this is source end, this is drain end. Throughout the entire end, the voltage or the effective voltage is constant throughout the entire length. So that's why I'm going to have same what is that, same density of electrons. Assume that you apply some voltage, so of course, as it is mentioned in this what is that, if you can, as it was mentioned in the video, let me also show you that. Where is that? Let me just, this actually looks like a resistor, where it went, one second. Maybe just before that. See here, this entire channel, because we know that this is a channel, so you can think of that channel like a resistor, because this is going to have some resistance for the current to flow. Assuming that this as a resistor, so let me go back to my camera and show you. Hey, sorry, where is my camera? This is my camera. Okay, this is a channel starting from source to drain. Assume that this is your resistor which is connected like this. Getting?
Yes, sir.
Now assume that I have applied some voltage between drain to source. So this current is now non-zero. So do you feel, since there is a current flowing here, from here to here you'll have some voltage drop, from here to here you'll have some voltage drop, from here to here you'll have some voltage drop. What I mean is, along the length of the transistor, does the voltage drop start increasing? Can you see the voltage drop is maximum here, here it is 0. This is what?
Yes, sir.
Along the length of the channel, the voltage drop, I'll call it as Vx, the voltage drop across the entire resistor channel length. So it is keep on increasing. See here, what is this? What is this Vx I'm writing? Vx is the voltage drop across the length of the channel because there is a current flowing. Correct? So in
Yes,
this
sir.
channel now, you have one voltage which is due to the current that is flowing in the channel, and you have one more voltage which is due to the applied gate voltage because of your VGS. Correct? So there is one
Yes, sir.
VG and there is one VDS and VGS. So what was actually V, that is gate to source voltage, when there was no current flowing? So as we discussed here, what was that voltage? Was it constant here throughout?
Yes, sir.
Throughout the entire length of the channel, the gate to substrate voltage was constant because there was no current flowing. When current start flowing, this is how the voltage is increasing. So effectively, so you have at each and every point of your channel, you have two voltage sources which are ineffectively making the electrons to be accumulated here. One voltage is due to this VGS, the other voltage is due to
Yes,
the drop across this entire resistor. So what is happening here is, if you can see this PDF, can you see this is Vx? It is increasing as the length of the channel increases from here to here. Can you see here? What does this actually says? Can you make out this? This is the effective Vg in presence of current that is flowing in the transistor. So when there is no current flowing through the transistor, you had this as the voltage. When there was no current flowing through the transistor, gate to substrate voltage was constant. When current is started flowing through this, the gate to substrate voltage is no more constant. It is no more constant. If it is constant, what happens? You're going to have the entire channel density, the electron density will be constant throughout the entire length. Since this voltage is not constant because of this existence of Vx, the voltage is actually now this minus this minus this. So what is this minus 0 here? You have same potential. What is this minus this? So you can see there is some reduction because this is increased. This minus this will be actually less and less. So what happens? You will have an effectively lower gate to substrate voltage in this region. So if you can see here, see in this, can you see this Vg, that is gate to substrate voltage, is keep reducing towards the larger, towards the edge of your drain?
Yes, sir.
What does this actually mean? What do you mean by gate to substrate voltage reducing? You have lesser potential for electrons to be get collected at the semiconductor oxide interface. So when the voltage is less and less, when the voltage between gate and the substrate is lower and lower, you don't have enough potential for electrons to be get accumulated. So that's why what happens, as you increase the potential of VDS, suppose if you increase the potential of VDS, does this voltage keep on increasing like this? So does this voltage keep on increasing? So why this Vx increases? Since Vx is ID into some R channel, does your ID increase as your VDS
ID.
increases? Does your
Yes, sir.
ID increase as your VDS increases? Because of constant channel resistance, this Vx will be keep on increasing as you increase your VDS. So what happens there? If there is no VDS, you can see the density of electrons is uniform throughout the entire channel. As you keep on increasing the what? VDS, the effective voltage at the drain side is start reducing. So when it start reducing, so you don't have a channel formation at this point. So that's why you'll have something like this type of structure. Where can I show you? Can you see here? See this? So can you say at this point of, for this particular picture, does the VDS is 0 here, exactly for this? Now, what will be the channel density of electrons over the entire length when VDS is 0? Will it be constant from source end to drain end? Reshma,
Yes, sir.
why? Why it will be constant?
No current
Perfect.
flowing.
Since there is no current flowing, the gate to substrate voltage will be constant throughout the structure. As the current starts increasing, where does the effective voltage in the gate to substrate reduces towards the drain end or towards the source end?
Towards the drain end.
Towards the drain end, the effective gate to substrate voltage reduces. So that's why you have fewer electrons compared to this side. So when does this will become zero? When does the substrate when does the pinch off actually happens? This will happen when the effective voltage here is 0 volt. The effective voltage, the drain will become 0 when VDS is equal to VDS SAT. So to be very clearly to say, so you have your channel between the source and drain. This is your channel. This will exactly cease. This will exactly cease at the drain side when VDS is equal to VDS SAT. That is VGS minus VTH. So this voltage we call it as pinch off voltage or saturation voltage. Now, if you further increase, what happens? If you further increase, what happens to that length? Can you see here? Can you
Length
see
decreases.
here it is that whatever you had 0, that will almost become negative, and you can see this 0 is extending towards this side. So whenever it is going, whenever you further increase your VDS, the pinch off will going to be more and more towards the source side. Can you see, assume that if this length was something like 10 micron, this length is 10 micron. So out of 10 micron, let me just take this as, let me show you this. Assume that this length was earlier 10 micrometer. Now, as pinch off starts, the channel length, assume that if it becomes 8 micrometer, correct? Why the channel length has reduced effectively from 10 micrometer to 8 micrometer? Why it has reduced? Physically it is there. You are not actually moving the drain to this side. Only thing is that channel has ceased. Channel has ceased. So in the expression of your ID, what do you have? Is your this is equal to W by L, correct?
Okay. Yes,
This
sir.
L is now L effective. So does the L effective reduces?
Yes, sir.
When does this L effective reduces? Okay, when does this 10 will become 8, it will become 9, it will become 7, and when it will become 6 micro? For what voltage of your VDS? Less
Greater
than,
than VD saturation.
more than VDS more than VDS sat. The question is now, when you are keep on increasing your VDS, so this was your entire channel length earlier, which was equal to, assume that 10 micrometer, 10 micrometer when VDS was 0, and it will be same 10 micrometer as long as this is less than VDS sat. Am I correct? Now
Yes,
assume
sir.
that VDS has increased beyond VDS sat slightly. So will it happen something like this? Can you see now? This effectively has become, assume that 9 micrometer. But in your expression, what do you have? ID is equal to Kp, of course, half W by L VGS minus VTO whole square. So this is true if this length is constant. But you can see earlier it was 10 micrometer, because what is this expression we wrote it as? This is the expression for
ID saturation.
ID sat.
ID.
We assumed in the initial the current remains constant anything beyond VDS sat. Correct? This is
Yes,
what we
sir.
assumed. But this assumption is wrong, because we never considered this variation in length of the channel. We didn't uh, consider this change in the length of the transistor. So it is not the physical length we are talking about. The effective length is no more this. The effective length actually reduces. So this is no more L. I will write it as effective. Does L effective reduces as you increase VDS? Reshma?
Yes, sir.
Yes, sir. Yes.
Okay, suppose if this L effective is reducing as you increase VDS, does this ID should increase?
Yes,
Because
sir.
it's in the denominator. So when some quantity in the denominator reduces, on the left hand side, you are supposed to have a increased ID, meaning
ID.
this was your ideal characteristics, but typically the characteristics goes like this. Can you see the current is increasing?
Yes, sir.
This current is increasing as your VDS increases, because you know that as VDS increases, L effective will reduce. The reduction of L effective will going to result in increase in ID. Can you see, as I increase the value of VD beyond VDS at, can you see the current is slightly increasing to a larger value? Can you see
Yes,
that this
sir.
increment? Now, this is this is due to what? This is due to what? This is due to what? Why the current is increasing?
Change in length or decrease in length.
Change in length of the channel. Correct? It
Yes,
is
sir.
happening due to what? It
Of
is,
phenomena.
it is happening due to the increment of VDS.
VDS is sir.
Correct? Now, are we actually changing the effective length of the transistor? Are we changing the effective length of the transistor in saturation region by changing the value of VDS? Hello?
Yes, sir.
So, what do you mean by, what is the other name for change? We call it as
Transition.
modulation. So, as you increase VDS, L will reduce. As you reduce VDS, L will increase in the
It
saturation
increase.
region. So, we call, there is a channel length modulation. Channel length modulation. This will happen in saturation region only. In saturation region only. So that's why it is in short form written as CLM, channel length modulation, due to variation in your VDS beyond VDS at, of course, in the saturation region. How do we account for, because you will not be knowing what is the value of L effective for each and every values of VD, because here you can see there is no term like VDS at all. There is no term VDS at all. But if you can see this typical graph, the current ID is a function of VDS. Is a function of VDS. So we will include this term VDS as well as the effect of this change in the length of the transistor in the new expression for ID as, so ID sat is now given by half Kp W by L, sorry, W by L VGS minus VTO whole square 1 plus lambda VDS. So this lambda is channel length factor. Channel length factor or channel length modulation. This is, the unit of lambda is volt inverse. Volt inverse. Now we can see this ID sat is a function of Kp W by L VGS minus VTO whole square 1 plus lambda VDS. So what is the least value of lambda you can think of?
Zero only.
If it is 0, what does it mean?
There is no variation in length.
Meaning it is an ideal characteristics.
Yes, sir.
If this lambda becomes 0, will it be something like this? So this is our ideal expression of ID sat without
Yes, sir.
considering channel length modulation. If there is a channel length modulation, then only this lambda comes into picture. Maybe in few problems we have considered lambda as 0. If you can remember the previous 1 or 2 examples, correct?
Yes, sir.
That
Yes,
means
sir.
the transistor doesn't have channel length modulation considered into effect. So then only this lambda becomes 0. If lambda is non-zero, then we consider the channel length modulation to effect. Then we have to use this exact equation. And you may can see in the textbook it is also said that, of course, it's explained that, okay, how does that electrons will going to continue their path towards the drain is because of high electric field between drain and source, so they'll be get attracted. Now the question is, where is that? What is channel length? Let me just show you that. I think it is somewhere here. Here. For lower length and okay, here. Can you see this? What is the impact of this?
Yes, sir.
Can somebody talk about this? You can see I have two transistors. Let me just say I have two transistors. Okay, let me show this. What does this say is, let me just have both of them. Uh, so don't worry too much about, of course, you need to know all these things. See here, what is the difference between this transistor and this transistor?
There's a change in length and width.
No,
Change in
Length and width.
length.
width. Is any change? You can't see the width at
No.
all.
Height. Yes, sir.
Actually, you cannot see the width at all because we're not seeing the 3D picture of it. 3D view of it we are not seeing. Only thing is that the first transistor L1 is lesser compared to L2. Correct?
Yes, sir.
Yes,
We
sir.
will define such type of transistor having lesser length as short channel Mosfet. This is long channel Mosfet. Correct? This is L1 which is lesser. This is L2 bit longer. This is a short channel. This is short. So the name of that device, it's still a MOSFET, but it is short channel MOSFET because the channel is short, and other one is long channel MOSFET. Can you observe what is the change in that output characteristics for short channel and long channel?
Yes, sir.
What is that difference?
Uh, in short channel, the variation is slightly higher when compared to long channel.
Oh, that's the exact meaning. So this was not a problem in earlier days. That is when the transistor got invented in 1960s. They were not having this channel length modulation effect because the channel length were large in nature. Now, once the channel length becomes lesser and lesser, now what is the channel length of the transistor? Anybody has any idea? What is the channel length of the existing transistor? Suppose if you buy a new what latest laptop. So what is the channel length?
So 18 Armstrongs.
Uh-uh.
It's in
Anybody bought new or latest
10
laptop?
micron.
10 micron. Okay. Anybody else? It is in terms of 7 nanometer. Armstrong, of course, we're not gone to Armstrong. This is 7 nanometer or maybe 14 nanometer. This is the length of the transistor. So one of your friends said it is 10 micrometer. Maybe this is maybe 20 years back or so and so. So that's what is the size of the channel length. So where is this 10 micrometer? Where is this assume that okay it is 10 nanometer? What is the difference here? Almost 10 power 3. This is 10 power minus 6, this is 10 power minus 9. So there's a 10 power 3 orders. There's a 3 order variation here. What I meant to say is when the channel length is large, so assume that there is a change from 10 micrometer minus 1 nanometer. What will be this? Assume that the channel length has reduced by 1 nanometer. Will it have a big impact on the channel length?
no, sir.
Assume from 10 micrometer it has reduced by 1 micrometer, sorry 1 nanometer. Will it have a big impact? Meaning here if it is like this for 10 micrometer, over here if it is 10 micrometer minus 1 nanometer, hardly there is no change. So
Yes, sir.
the channel length modulation is very minimal. You consider the same thing, you have a 10 nanometer and minus 1 nanometer. Can you see the variation is still 1 nanometer, but you can see the overall length. Earlier it was 10 micrometer, now it has become 10 nanometer. So 1 nanometer is very significant, almost 10% of 10 nanometer. That's why you can see a huge impact on the characteristics of the device when the length of the transistor is lesser and lesser. So that's why we have this effect. The variation is more as the channel length reduces. So all these channel length modulation effects coming to picture only for short channel devices. They are not there in long channel devices. So whenever the value of lambda is given as some non-zero value, we have to always use the expression id is equal to half of course especially in saturation region, ID sat is equal to half into Kp W by L VGS minus VTO whole square 1 plus lambda VDS. This is not VDS at, it is simply VDS. So lambda is varying from 0.1 volt inverse to 0.01 volt inverse. So this 0.01, is it for short channel or long channel? So which one is for short and long channel? So if I say short and long, this is short and long, which one shall I strike out? For 0.1 volt inverse, is it for long channel or short channel?
Short channel, sir.
Sure.
The variation is more in there, right?
Variation is more, so if the value of lambda is more, then it is short channel. If the variation of lambda is less, then this is meant for long channel. Get it? If it is 0.01, if it is 0.1, the variation is okay. Assume that this is ideal, so this may be for 0.01. If I write it for, this may be for 0.1. This is for volt inverse lambda, volt inverse lambda. If lambda is, this is what? Lambda equal to 0. First one is lambda equal to 0, second one corresponds to 0.01, the third one corresponds to 0.1 volt inverse. Is that clear? What is there on x-axis? It is VDS, on y-axis it is ID. Done? Let us see the impact of that in the LT spice. Shall we see that? When
Yes,
we
sir.
see the
Sir,
impact
how
of
this lambda value is calculated?
lambda values are calculated, it will be actually given by the foundry people. When I say foundry people, when the people actually manufacture this one, wherever they manufacture, it is a parameter that is measured and given to us. So you cannot, of course you can theoretically certainly get it, but actually what to substitute will be given by the foundry people. But in simulation purpose you can edit any value. This lambda value will be given by the foundry people for a given technology. What should be the value of lambda? So it is actually given by the foundry people who actually manufacture the transistors. Let me just go to LT spice, and then where is LT spice? Okay, I think I may have to share this also. Are you seeing this LT spice?
No, sir.
Okay, let me share this. Is this now?
Yeah, yes, sir.
Okay, let me take LT spice. Let me take a device in Mosfet. Sorry, this is there. Shall we do an IV characteristics now? If I do IV characteristics, what are things required? So I need to have two voltage sources, one here, the other here, and then let me connect it through. Okay, initial few classes is hard for all of you to understand. Okay, once you understand all these things, of course it requires repeated reading, asking doubts and all those things. If you don't ask any doubts, okay, how do we know, okay, what is the problem with you people? So make sure that you are there on your toes, and then let me make this 1 volt. Let me make this also 1 volt. And what I should do if I want to do a trans output characteristics, which sweep?
DC should be good.
DC sweep, which one to sweep now? It is V2
V
0 to maybe 2 volts with an increment of 0.01. Okay, done. It's placed here now. I can do this. Oh, sorry, I have not edited. I didn't add that model file. Let me add dot model nmos kp equals
200 U
200 u comma
with
vto equals
0.4.
0.4, and let me put lambda lambda equals 0.1. This is what is lambda. you have to type lambda, which is the channel length modulation factor. Now you run it. Let me run. Say this drain current. Can you see this variation? Let me minimize this and then put it here. Can you see this is keep increasing?
Yes, sir.
I can see now. You can put on more cursor. See here, or the current is changing. One, it is here, it is 38 micro. Okay, let me also edit the dimensions. I didn't edit the dimension. Let me edit the dimension of the transistor also, because we need to verify now. How do I put it? So let this be 10 micro and let this be 100 micro. Done. Okay, it's
Yes, sir.
done. Let me run. Okay, now fine. Can you people find out what is the exact value of current that we are getting? So you can take the values of VDS also. So what I have now is, let me show my camera also, so that you can able to verify what is the current that I'm getting. Is it correct or not? Okay, what are the expression I have? This is the expression for so and so. What is lambda we have taken? 0.1. You can take lambda as 0.1. In the first case, what is the value of VDS? Here it is 420. Correct? Sorry, it is 671. In the first case, put it as 671 millivolt. The second case, what is the second case VDS? Hello, hello.
Yes,
Who
sir.
is
We
there with
haven't.
me? Is it not
One
visible?
point.
1.69. So we have VDS one value as 0.671. The other value of VDS is 1.692. What is corresponding ID? Take lambda is equal to 0.1. Lambda is equal to 0.1. What is VGS, VDS? All those things are there. VGS is equal to 1 volt. VTH is equal to 0.4. Give me this. Let me also do simultaneously. It is now 0.5 into 200 exponential minus 6 into 0.4 square into 1 plus 0.1 into 0.1 into 0.671. Is it correct? Hello, hello. Who is there with me?
Sir.
How much is the value? Substitute and calculate. Hello.
4.15.
4.15.
384.15.
Okay, that is fine. Okay, 384 microampere are you getting here? Can you see for the first one it is 384 micro. For the second one you substitute VDS as 1.69, find out what is the current. Is it close to 420 microampere? Because now what we are trying to see is, even in saturation region the current is not constant because of lambda. Substitute the values.
Four 20.8.
Okay, 420.8, that's fine. Okay, can you see it's almost 420.93? Can you see the
Yes,
currents
sir.
are almost matching? 1 plus. It's 420.84 microampere. Okay, let me ask one of your friend to show the values.
So it is 3.84 micro, sir. 38
3.84.
micro, sir.
Come again.
38.4 micro.
Which one?
Second one, sir, for VDS 1.692.
Just calculate lambda is equal to 0.1. It's not 0.01, it is 0.1.
Okay, sir.
What did you substitute?
0.1, sir.
Just do it again, redo it again.
Yes, sir.
Are you all getting? Let me just ask one of your friend to just show the Bhavyashri. Why don't you show the answers?
Sir, I'm doing, sir.
How much time you require, say? Just entering the values. Harini? Harini? Harini?
Yes, sir.
Who is this? Harini? Yeah, show me the values. Harini? What are the values?
Sir, I got 384 microampere.
That's correct, no?
Yes, sir.
What is when for the other value of VDS?
Sir,
For VDS is equal to 1.69. What are the values?
sir, 1.6 I'm still doing.
How much time you require, madam? If this is the pace, it's difficult, no? Assume that you have only 1 minute for each of the question.
420.6 millivolt.
Correct.
Milliampere.
It is 420 microampere, not milli.
Okay, sir.
Okay, Hari Prasad. Show me your answer.
Sir,
Show me your answer.
so I am getting the wrongly, sir. 0.21 microamp I am getting, sir.
Type it. I want to show you. I want to see your calculator. Show me your calculator.
Yes, sir.
Turn on your camera. Turn on your camera. All of you turn on your cameras. Let me see. You are not high school girls and boys, so that I need to check all your answers. So you should be on your toes.
So what is the value of W by L?
That you should know, man. What were you doing? Okay, when I was substituting W and L's. Huh? Were you sleeping or what? W we edit as 100 micro, L as 10 micro, no? How much is W by L then?
10, sir.
Then? You have to be attentive in the class. Hari Prasad.
Sir, okay, camera on, sir.
It's not visible.
Sir, it is on, sir.
I can't see you.
So calculator, I am showing calculator, sir.
Okay, how much is the value you are getting?
So some mistake I done, sir. I will correct, sir.
Do it fast.
For 20 micro, sir.
Who is this?
Anjum, sir.
For the second value. For the first one?
Sir, for 1.69, it is 420 micro, sir.
First one? For 671?
So 332 micro, sir.
Okay. Who is Kirtana? Kirtana.
Hello, sir.
Yeah. What are the values you're getting?
Sir, for 1.692, I got 418 microampere.
Then for the other value, 671 micro. Sorry, millivolts.
So 671.
Okay, Hari Prasad, what you are showing is now.
Calculator, sir.
Okay, what's the value? Are you getting proper value?
Yes, sir. Yes, sir. If I shift the 3 decimal place, 38 millivolt, sorry, I will get correctly, sir.
Okay, that shifting and all those things, why do you do? You edit the proper values, you'll get it correctly. Shifting and all those things, you can just, you put it to engineering, it will give it as 380 microampere, whatever, it will give micro value correctly. So no need of shifting and all those things. Okay, done.
Okay, sir.
Kirtana, what is for the second value?
Can I switch off the camera, sir?
Yeah. Again, not happy with all of you that okay, you're not on your toes. So make sure that okay, all of you are making the calculations before I complete the question. It doesn't take too much time, no? Okay, from next class we will consider the value of lambda as non-zero and then try to solve the problems and then move on to the next topic of CS amplifiers. Okay, maybe tomorrow by around 5 o'clock we're going to have a quiz on the topic that we have covered so far. Okay then, thank you.